Hello friends, in this video we are going to revise the subject fluid mechanics, covering all the topics of this subject and all the formulas and concept in this video. Okay, what is actually a fluid mechanics? Fluid mechanics is the study of the fluid behavior at rest and in motion. Now what is a fluid? Fluid is a substance in liquid or gaseous phase. They are capable of deforming continuously under the action of shear stress. Like we know what is the fluid. Fluid may be a gas or maybe a liquid. Now in solid, the shear stress is directly proportional to strain. We are very much familiar with this. But in fluid, the shear stress is directly proportional to the strain rate. That is rate of change of strain with respect to time. Okay. Now there are few terms which we have to memorize. What is vapor pressure? Vapor pressure is the pressure exerted by the vapor on its surrounding. Okay, pressure exerted by vapor on its surrounding. What is saturated vapor pressure? The vapor pressure when air is having maximum moisture holding capacity. Okay, that is the maximum moisture holding capacity. The vapor pressure at that point is called saturated vapor pressure. Now what is the cavitation? Cavitation is when absolute pressure falls below saturation vapor pressure. Then the vapor bubbles are created. Like we can see in this case in the pipe. Actually this is at low pressure zone and this is high pressure zone. When the liquid moves from this place to the upper place, at this upper portion, then the pressure will be reduced. Okay, so this absolute pressure falls below the saturation vapor pressure and the vapor bubble is created. When this vapor bubble comes to the high pressure zone, now these bubbles get bursted, and they cause some kind of noise, vibration, surface pitting, etc. I mean they will damage the pipeline. Okay, that is why cavitation is harmful for our pipe. Okay, the absolute pressure is equals to atmospheric pressure plus gauge pressure. Gauge pressure is the pressure which we can measure by our measuring instruments. Okay, next concept is bulk modulus K. We must be familiar with it in SOM. Bulk modulus equal to minus of dp upon dv by v, that is rate of change of stress upon this is pressure is the stress, and upon rate of change of volume, I mean this change of volume upon total volume. Okay, we can also write it down like this is the density into dp upon d rho dp upon d rho. Okay, now the compressibility equals to 1 upon bulk modulus. We can write the formula of this like this. Okay, now next topic is viscosity. Viscosity is very important topic in fluid mechanics. Viscosity is the measure of resistance of fluid to deformation. Okay, this is the resistance, that is the resistance offered by the solid is normally friction, and if the frictional force in fluid, then we will call it as viscosity. Okay, between different layers of liquid, we can see it here that this is the one layer and this is the second layer. Okay, the distance between these two layers is dy, the velocity difference is du. Okay, in this case we can see here that for Newtonian fluid, that is Newtonian fluid like water, air, gasoline, oil, etc., we have the shear stress equal to mu du upon dy. Mu is the coefficient of viscosity. Okay, usually we call it viscosity, and du upon dy. Mu is the dynamic viscosity coefficient. Okay, du upon dy is the rate of change of velocity with respect to this y distance. Okay, now unit of dynamic viscosity is Newton second per meter square or poise. 10 poise equal to 1 Newton second per meter square. Okay, now we should remember here one thing, that mu, that is the dynamic viscosity of water, is 50 times dynamic viscosity of air. Okay, and with increase in the temperature, the dynamic viscosity decreases. Okay, this happens in the case of liquids only. Okay, in the case of gases, the case is just reverse of it. Now for other fluid other than Newtonian fluid, this shear stress equal to A du upon dy raised to the power n plus b, where a and b are the constant and n is the power to this rate of change of viscosity. Okay, now we can see a graph for it. This is the graph. This is very important graph in fluid mechanics. We can see it here. This is graph between shear stress and rate of change of velocity. Okay, du upon dy. between the different layer. Here we can see that for Newtonian fluid we have B equals to 0. That is, what is B here? B is this value, this constant value. Okay, this is 0 in the case of Newtonian fluid. For dilatant fluid and for pseudoplastic, for all these three, B equals to 0. That is why this curve is starting from 0 here, and this slope, that is n, that is the power of the rate of change of velocity. This is when this is less than 1 we are having pseudoplastic, when this is greater than 1 we have dilatant. Okay, now there are other cases when B is not equals to 0, then and n equals to 1, that is a straight line is formed, then Bingham plastic. Okay, now, this is the linear behavior. Now if this is increasing behavior, n is greater than 1, then it is a rheopectic, and if n is less than 1, then this is thixotropic fluid. Okay, moving ahead with kinematic viscosity. For kinematic viscosity equals to mu upon rho. Okay, dynamic viscosity upon density. Unit is meter square per second or stoke. Okay, 1 stoke equal to 1 centimeter square per second. Kinematic viscosity of air is 15 times kinematic viscosity of liquid. Okay, this is the reverse of that case. There was dynamic viscosity of liquid was 50 times dynamic viscosity of air, and now kinematic viscosity of air is 15 times kinematic viscosity of liquid. Okay, with increase in the temperature, kinematic viscosity increases for air, and with increase in temperature, kinematic viscosity decreases for liquid. Okay, next topic in our syllabus is surface tension. Surface tension is tension developed at the surface of liquid due to cohesion. Okay, we can see it here. This is the particle, this is the cohesive force that is attracting this molecule. Okay, so this process is called surface tension. Now for a thin film, we must have seen this case. This is the length of this film. Okay, this is the wire, and this is the bubble or the film. Okay, now if we apply a force and we have to find out the surface tension here, then this surface tension equal to the force applied upon 2L. Why 2L? Because we are having two layers, two surfaces of liquid like this. If we see the cross section, we are having two surfaces. One is this one and another is this one. Okay, upper surface and lower surface. That is why F upon 2L. Okay, so another formula for surface tension is the work done upon change in area. Okay, the work done to bring this this wire from this position to this position upon area. Now the application of surface tension is pressure difference calculation. For the drop of water in air, we have delta P equal to 4 sigma upon D. For soap bubble in air, we are having a case of 8 sigma upon D. This is delta P equal to 8 sigma upon D. For liquid jet, delta P equal to 2 sigma upon D. Okay, where sigma is the surface tension and D is the dia of the soap bubble or the drop of water or the liquid jet. Okay. Next topic is capillarity. Capillarity is the consequence of surface tension and adhesion. The capillarity is the rise of liquid in small dia pipe inserted in liquid. Okay, like this. If we insert a small dia pipe into this liquid, then the rise of this liquid is called capillarity. Okay, depression is the fall of liquid in the small dia pipe inserted in the liquid. If this is another case in which if we insert a pipe and this water surface gets down, okay, like this. This is the case of depression. Okay, here we have the phi equals to contact angle, phi or theta. This is the contact angle. If this is usually less than 90 degree for this action of capillarity. Okay, now if phi is less than 90 degree, that means adhesion is greater than cohesion. Adhesion is between different medium, like between liquid and solid, and cohesion is between same type of particle, like between liquid and liquid, between gas and gas, between solid and solid. Okay, so if phi is less than 90 degree, then adhesion is greater than cohesion. Then there will be the rise of what of the liquid, and liquid will wet the surface. Okay, now the rise in this case, when there is liquid between two plates, okay, then we are having H. This is the rise equals to 2 sigma cos theta upon gamma t. Okay, gamma is the unit weight of this water and T is the thickness of this thickness of liquid between these two plates. Okay, theta equal to this contact angle and sigma is the surface tension. Next topic is fluid pressure and its measurement. The fluid pressure, we are having units here. Some units we have to memorize. 1 pascal equal to 1 Newton per meter square, megapascal 1 Newton per mm square, 1 bar equal to 10 raised to 5 pascal, 1 atm equal to 101.325 kilopascal, 1 kg per centimeter square equal to 9.81 Newton per centimeter square, 1 atm equal to 14.690 psi pound per square inch. This is not of very much huge in our syllabus. Up to this point we have to memorize all these values. Okay, now the atmospheric pressure. What is atmospheric pressure? This is the pressure exerted by the atmosphere on some body. Okay, standard atmosphere at mean sea level. Okay, that is 0 MSL. MSL is at Bombay High. Okay, local atmospheric pressure equal to atmospheric pressure at other location other than mean sea level. The standard atmospheric pressure, the value is 1.013 bar or 10.3 meter of head of water or 76 centimeter head of mercury. Okay, we must remember this value, that is unit weight of mercury is 13.6 of unit weight of water. Okay, now the absolute pressure is with respect to the complete zero or vacuum. That is absolute value, but the gauge pressure is with respect to local atmospheric pressure. Okay, the difference between local atmospheric pressure and the absolute pressure is gauge pressure. Okay, all pressure measurement equipment are calibrated to read the gauge pressure only. Okay, how this is determined? In vertical direction, P equal to rho g z. If the liquid filled like this and this is the z distance and we have to find out the pressure here. Okay, at this point P, then P equal to rho g z, where rho is the density of this liquid, g is the acceleration due to gravity. Now the pressure measurement devices, we have different devices here like barometer, manometer. Barometer is just simple instrument. We call it as Torricelli barometer. We can see it here. This is the case of barometer. We are having a U-tube here. Okay, this is vacuum filled and this is the rise of water. Now we can find out the pressure by the simple formula as we have memorized earlier. Okay, P equal to rho gh. Now we have to keep remembering here that this is the mercury, not the water. Okay, so density of mercury should be taken at this point. Okay, next is your manometer. There are two types of manometer, either simple or differential manometer. Simple manometer is of three types: piezometer, U-tube and single column, while differential measurement is a single differential to find out the difference between the pressure of 2 points. Okay, simple manometer, we are having the first type as piezometer. Piezometer is just attached to the pipeline like this. Okay, this is the same liquid is rising as it is flowing in the pipe. Okay, and we find out this H, and pressure is determined at G gamma W into H. Okay, in the case of U-tube manometer, we are having a U-tube like this and a different liquid is filled in this portion. This is having G2, that is manometric liquid. Okay, and then if we have to find out the pressure at this pipeline, then we can find it out like this: G2 gamma W H minus G1 gamma W X. Okay, next is our single column manometer. Okay, in this one we are having a single column like this. Here we are having this first this is second liquid and this is the first liquid, that is same as the liquid flowing in the pipe. Okay, now in starting we are having this level like this at A. Okay, and when pressure is applied, then this level just moves down by delta Y value and this liquid rises here by amount H. Okay, area of this tube is A, small a, and area of this portion, larger portion, is capital A. This distance is Y1, and here the value of pressure at A, by using the formulas and the calculation, we get the result of PA equal to G2 gamma W H. G2 is the specific gravity of this liquid, gamma W is unit weight of water, and H is the rise of this liquid, this manometric liquid in the tube, in this smaller dia tube. Okay. Now the differential manometer used to measure the difference between the pressure between these 2 points A and B. Okay, we are having a manometric liquid as this G2 of specific gravity G2, and G1 is the specific gravity of the liquid flowing in the pipe. So to determine the pressure difference, we use the formula PA minus PB equal to G2 minus G1 gamma W X, where X is the difference in the level of this manometric liquid from this point to this point. Okay, that is alpha minus beta. Next topic is hydrostatic forces on plane and curved surface. Here we can see, here this is the plane surface. Okay, and the hydrostatic force here is gamma h1 at this point because this is h1 height, and gamma h2 at this point because this height is h2. Okay, this is simple concept. But on the curved surface, one thing which we have to memorize here, that same direction of the forces, this is same direction, each force is parallel to each other. Okay, but in the case of the curved surface, all these are perpendicular to the surface of this this body. Okay, so different direction of forces are here. We can see it here, gamma h1 to gamma h2. Okay, if we have to find out the center of pressure, at which depth we are having the center of pressure, then we can use this formula, S equal to h bar plus IgG sin square theta upon a h bar. H bar is the height of the CG from the top of the surface of water. Okay, SC is the center of pressure, height of center pressure from top, and this is the theta angle of this body on which the pressure is applied. Okay, area is the cross section area, sorry, this area of the surface which is in contact here with this water. Okay, and IgG is the moment of inertia of this surface having this axis, like axis going like this. Okay, now the next topic is liquids in relative equilibrium. When liquid is in stationary phase, then we are having pressure equal to rho gh, but if it accelerating in upward direction, then this PA equals to rho g effective into h. We will take g effective here, and g effective will be g plus a2. This is the acceleration in upward direction. Now the horizontal and vertical acceleration, here we are having a case of theta here, like this is moving like in this direction with some acceleration ax. Okay, then and g is acting downward, and this whole body is moving in this direction, and a liquid filled here having this much of height. Okay, now we have to determine the pressure at some point, like at this point A. Then this is equals to P into G effective into H. Okay, this is P into G effective into H. Okay, so where here the value of theta, that is tan theta, equal to ax upon g plus ax, and we can find out like this also, if we want to determine this height. Okay, this is also we can find out because we know this value. This must be some value like d. Okay, this is value h, then h upon d equals to tan theta. Okay, by equating this we can find out this height, the rest of the height, whatever we want to determine, we can find out here. Okay, next topic is rotation in container. This is the container rotated by omega, and at the distance r we have to find out some pressure, and using the simple values we have determined earlier, we can find out this increase in the height as z equals to omega square r square upon 2 times g effective. Okay, r is usually we are taking capital R. Okay, or if we have to determine the height at some other place, then we will use the small r value, that is this value up to the point under consideration. Okay, now the pressure at A equals to rho g effective into h, and h height will be taken from the surface of the liquid, the actual surface of the liquid. Okay, now at every point on the free surface the pressure is 0. Now the volume of paraboloid of rotation, this is the paraboloid here, and this volume is pi r square h upon 2. If we are having a cylinder, we are having the volume as pi r square h. Now this is half of that. Now rise above the original level equal to fall below the original level. This is the basic concept we will use to find out the spillage of the water. Next topic is buoyancy and flotation. What is buoyancy? Buoyancy is the resultant force exerted on the body by static fluid in which the body is submerged or floating is called the buoyant force. Okay, always vertically upward force. This is the buoyant force, and Fb is the weight of liquid displaced by the body. This is in the simple term. We find out the buoyant force like this. You must be familiar with buoyant force. Stability of the submerged body. Equilibrium. There are three types of equilibrium: stable, neutral, and unstable. We can see the case here. This is case of stable, neutral on the plane surface, and unstable on the convex surface. The linear stability, when the linear displacement sets up, restoring force, the body is said to have linear stability. Okay, when any body is submerged in water like this, okay, and there is a force upward and providing it a linear displacement, then it is called linear stability. The rotational stability, when a small angular displacement sets up restoring couple like this. Restoring couple, in this case, if we are having a body like this, the more of the weight is in the downward direction here at this down place. G is here. Now when it is rotated like this, we are having G dash here and W here, and this distance, the B G bar sine theta, this distance is B G bar sine theta. Okay, so the restoring couple will be W B G sine theta. B is the center of buoyancy, G is the center of gravity, theta is the angle of rotation, okay, and W is the weight of this body. Now if B is above G, then stable equilibrium. If B is at G, neutral equilibrium, and B is below G, unstable equilibrium. We can see it here like this. Another concept arises here of the meta center. Okay, this is the body in original form. When this is rotated, the center of buoyancy shift here, and the center of buoyancy will make some will cut this line joining B and G earlier. It goes like this and it cuts at some place here. This place is called this point is called meta center. Okay, so we can see it here in the line representation. M is here, G and B. This is the theta by the rotation, and this GM is called the metacentric height. Okay, and the restoring couple is WGM sine theta. Now the first case here is if M is above G, the value, if M is above G, then BM is greater than BG. That means GM equal to BM minus BG, which is greater than 0, and the case of stable equilibrium. If M is below G, then BM is less than BG, and GM equal to BM minus BG is less than 0, case of unstable equilibrium. Okay, that is GM, okay, GM equal to BM minus BG, and this is less than 0, that is unstable case. If M is at G, then BM equal to BG and GM equals to 0, and neutral equilibrium case will arise here. Now how we will find out the BM value? BM equals to I upon V. Okay, here I is the moment of inertia of this plane that is in contact with, if we see it from the top, then we can see if it is a rectangular plane, then it is like this. So moment of inertia of this plane. Okay, this we are having like this axis. Okay, and we will find out the I from this surface that is at the verge of submerging. Okay, so and volume is the volume of this solid body inside the liquid. Okay, now we are having the fluid kinematics. Kinematics is the study of the fluid in motion, like velocity, acceleration, angular velocity, etc. Methods: Lagrangian approach concentrate on individual particle in the motion. Okay, and we study its velocity, acceleration, etc. Means if we are having a liquid flowing in this and we are concentrating on the single particle only, then this is Lagrangian approach. But the Eulerian approach is concentration on finite volume. Okay, this finite volume is called control volume or CV. At one point in control volume, study of velocity, acceleration, etc. is done. Okay. Now the types of flow: steady and unsteady flow. Rate of change of velocity with respect to time equals to 0. Acceleration, pressure, these are with respect to 0. This is the case of steady flow, but in the case of unsteady flow, these are not equals to 0. Uniform flow, rate of change of these parameters with respect to space is equals to 0. Okay. In laminar and turbulent flow, in laminar flow, the fluid motion is such that one layer slide past the other. That is called laminar flow. Okay. One layer of liquid, this is one layer, this is another layer, this layer slide past this layer. Okay. We can see it here, laminar. If this is the boundary surface, then we are having velocity distribution like this. Smaller velocity is near the surface, this is zero velocity, and this is increasing in upward direction. While in the case of turbulent flow, there is intermixing, so we are having the graph like this. Now in laminar flow, no momentum transfer between layers, but in the turbulent flow, intermixing and momentum transfer occurs in turbulent. Okay. Now the effect of viscosity is large in laminar flow, effect of viscosity is small. Okay. Usually laminar flow is due to the viscosity only. Now effect of viscosity is maximum at boundary, so flow near the boundary is laminar, like here. In the case of boundary, we are having the flow as laminar flow. Now in turbulent flow, u equals to u bar plus u dash. We can see it here. What is u bar? U bar is temporal mean velocity. Like this mean velocity, like if we are having a graph of velocity versus time, then this mean velocity is u bar, that temporal mean velocity. U is the instantaneous velocity, and u bar is the fluctuation component, like this. This is the u dash value, sorry, u dash. Okay, these fluctuations are represented by u dash. Now flow at high velocity are generally turbulent. Okay, high velocity flow, intermixing will be there, so this is turbulent. Next topic is rotational and irrotational flow. When fluid particle rotates about its mass center during movement, okay, rotate about its axis like this. Okay, then this is rotational flow. The forced vortex is rotational flow, and the free vortex is irrotational flow. You must be aware with the vortex flow like this, helical shape. That flow, when we are applying the external force, then this is rotational, and in rest of the cases it is free. At boundary layer like this, flow inside boundary layer is rotational. This is the viscous region here. This is rotational flow. Outside, that is in the inviscid region, we are having irrotational flow. Okay. Now the flow visualization. There are different types of line for flow visualization. First one is streamline. Equation is dx upon u equal to dy by v equal to dz by w. This streamline is represented here like this. If we are having the flow path, this is the flow, and if this is a curved path, then the tangent at a point, this velocity. Okay, this is representing the streamline. We are having tangent at different point. This is the theta value. The tangent to the streamline at any point represent the direction of the velocity at that point. Okay, so there is no component of velocity perpendicular to the streamline, since velocity is always tangential to streamline. Okay, velocity is always tangential to streamline, so we are not having any component in this direction. Okay, now set of streamline equal to stream tube like this. We are having different streamline from point A to point B. Okay, so this whole of the mass of the fluid is called stream tube. Next is our path line. Path is the actual path traveled by the fluid particle over some time period. Okay, like this is the fluid particle. At t1 time it is here, at t2 time it is here, at t3, at t4 time it is at these places. Okay, so this the whole line is called path line. Now the streak line, locus of all the fluid particles that pass through a fixed point is called streak line. Okay, if we are having some fixed point like this and find out the locus of all the particles, then this is the streak line. Streak line can be formed by induction of dye or smoke from a point in a flow. We will form a streak line. We must have done this practical in our in our graduation or in our diploma. Okay, for steady flow, streamline, streak line and path line are same. Okay, now continuity equation. Next topic is continuity equation between in 1D and 2D and 3D flow. In 1D flow, we are having curl by curl T rho A plus curl by curl S rho AV equals to 0. And for steady flow, we are having this curl by curl T equals to 0 only. This term becomes 0. So we are having this term only. Here we are having the rho AV as constant, because this is differentiation of this term equals to 0. We can write it down here like this: rho 1 A1 V1 equal to rho 2 A2 V2. For steady incompressible flow, that is rho is not changing from one place to another, then A1 V1 equal to A2 V2. Now for 2D and 3D flow, we are having d rho by dt plus or curl rho by curl t, curl by curl x of rho u, curl by curl y of rho v, curl by curl z of rho w equals to 0. Now the for steady incompressible flow, steady flow, this term becomes 0, and for incompressible flow, this rho value becomes 0 from one place to another. Then we are having del u by del x, del v by del y, del w by del z equals to 0. Okay. Next is the acceleration of the fluid particle. Dv by dt equal to axi plus ayj plus azk, where ax is del u by del t plus u del u by del s, v del u by del y, w del u by del z. Similarly, ay and az are written. You can see it here like this. V value is being kept under the partial differentiation. In this, the term du by dt, dv by dt, dw by dt, that is the rate of change of velocity with respect to time, is called temporal or local acceleration, and rest of these terms with respect to space is called convective or advective acceleration. Okay. Now the normal and tangential acceleration. A is equal to v dvs upon ds plus dvs upon dt. Here we are having a streamline like this. This is the normal component of velocity at some point, and this is the tangential component. Then we are having the tangential component as A is equal to dvs upon ds plus dvs upon dt, and v is outward. Okay. Now an equals to, that is normal component, equal to v dvn curl vn upon curl s plus del vn upon del t. Now in this also we are having first term as convective or advective acceleration, and second term with respect to time is local or temporal acceleration. Here we have to memorize few things, like these questions were asked in GATE. If we are having lines like this, okay, and going out like this, these are straight lines, and diverging lines, then converging lines. Here we will have the tangential component of acceleration, because tangential component of acceleration moves in the forward direction, but we are not having any normal component here, because we are not having any component in this direction. Okay, this we are not having here. But in this case, like these parallel lines in the curved, these are curved parallel lines. Here we are not having any tangential component, but we are having normal components, okay, of velocity. When this is neither this is converging and diverging, plus this is curved also, here we are having both tangential plus normal component also. Next topic is our angular velocity. Angular velocity equals to omega xi plus omega yj plus omega zk, where omega is equal to half of del w by del y minus del v by del z. Omega y is half of del u by del z minus del w by del x, and omega z equal to half of del v by del s minus del u by del y. Now we can write it down like this also in the matrix form. If the flow is irrotational, then the angular velocity equals to 0. In 2D flow, in xy plane, if flow is irrotational, then omega z equals to 0. And we can write it down like this also: del v by del x minus del u by del y equals to 0. Then this term will be like this: del v by del x equal to del u by del y. Now the vorticity is 2 times of omega, that is 2 times of angular velocity. Now we can write it down like this also: curl of velocity, del cross v. The vorticity is, if the vorticity equals to 0, then the flow is irrotational. Next is circulation. Circulation equals to an integral of v dot ds. Okay, if circulation equals to 0, that is around, if circulation equal to 0 around a circular curve, then the flow is irrotational. Okay, what is circulation? Actually, circulation is the line integral of tangential component of velocity vector along a closed curve, means along this curve. closed curve. Okay, circulation per unit area, we call it as vorticity. Next topic is velocity, potential and velocity function under the fluid kinematics. This is velocity potential function of x, y, z and t. This is a scalar function of space and time. Right, we can write down it like this also. U equals to minus of del phi by del x, v equal to minus of del phi by del y, w equal to minus of del phi by del z. Now, usage of this velocity potential is it helps in integrating Euler's equation to obtain Bernoulli equation. If velocity potential exists, that means it is an irrotational flow. If velocity potential equal to 0, okay, then this is rotational flow. Now the flow is always occurs in the direction of decreasing velocity potential. Okay, the direction of the flow will be from higher velocity potential to lower velocity potential. Okay, a Laplace equation using velocity equation can be written like this: del square phi upon del x square plus del square phi upon del y square plus del square phi upon del z square equals to 0. Okay, this is used many a times for the calculation purpose. Next topic is stream function. This is a scalar function of space and time like velocity potential. The difference is that here v is equals to del phi by del x and minus of u equal to del phi by del y. Okay, we have to memorize this, like here v and x, u and y. Okay, and this negative sign. Okay, we can see it here, y this is like this. This is the velocity potential function in x direction. If we differentiate in the x direction, then we will get the value of v in the perpendicular direction of it. If we differentiate with respect to y, then we will get the negative of the value of u, that is in the negative x direction. The Laplace equation is similar to the velocity potential's Laplace equation for 2D. Now for every point on a streamline, this stream function has a constant value. Okay, this is very important. Now the flow, here we can write down the flow as phi a minus phi b, and this flow is in the perpendicular direction of this phi. Okay, the streamline is always perpendicular to equipotential line. Equipotential line is the line of having equal potential throughout. Okay, so in this video we are taking a pause here, and in the next video, that is the part 2, we will discuss the rest of the topic of fluid mechanics. Okay.